Hello, we are coming from Group 6 for Assignment 2 on Advanced Surface Modification for Metallic Material. So Group 6 assignment is mainly on ceramic hard coating onto cutting tool. So we look into our introduction. So in a manufacturing process requires the conversion of raw material into finished good on a large scale and also a repetitive scale. So there are 7 pillars in a manufacturing process. So in this assignment, our main focus is for machining. So in machining, some of the machining processes that we know is drilling, turning, milling, boring, and grinding. So if over here we look at it, we are looking at machining. That is the removal of material into the desired shape. So in 1990s, in the 90s, the high-grade steel is usually used for the cutting tool, but the limitation of high-speed steel is that it only operated at a low speed, that is 100 square feet per minute, due to the overheat and the deformation from the chemical interaction with the workpiece, meaning the cutting tool and the workpiece. So the solution, how do they cater for high-speed tool is that they use tungsten carbide, that is WC. Ceramic was developed that able to operate the cutting tool at a higher speed that is 300 square feet per minute, that is consisting of cement or sintered carbide. So the limitation of WC, that is the tungsten carbide, the cement is limited by the softening and the chemical degradation in the metal bond phase. So what are the solution? They use aluminum oxide, or they known as alumina, that was developed to maximize the speed at 1000 square feet per minute. But the limitation of alumina is actually they fracture due to the brittleness of the material at high temperature. So the solution is titanium carbide was added to alumina for the ceramic to ceramic matrix that able to reach up to 3000 square feet per minute on the cutting tool. So if we look over here, the cycle, we will start over here, the two contact with the substrate, the material. Then at higher stress, frictional heat already generated, then it will lead to corrosion or erosion. So we look at why ceramic is chosen. Because of these four properties, we look into the mechanical property due to the high hardness, high deformation resistant, high fatigue resistant, and also high fracture. For the thermal property, we are looking at high thermal conductivity, high thermal shock, and over the chemical composition, we look into one of the property here, and the tribological property that is on the wear resistant and the adequate lubricity. So what is ceramic? As we know, ceramic is what we are conventionally known is that ceramic is usually come from the traditional portion, that is from the cement, whiteware, clay, brick and tile, abrasive, and refractories. So you can see here, in BM they call the period belanga or something like that. But ceramic in engineering, we are looking for oxide, silicate, carbide, and nitride, meaning this element is in the ceramic component. So we look into the first portion. What is the surface requirement for the component? The first one will be the surface roughness. So adequate rough surface allow the enhancement of the addition. That is, if we look over here, the portion that is the slide over the portion, the image here, a simple interlocking between the rough surface and also the part coating flow and solidify in the crevices. The crevices is over here, like the what we call it the longkang. Then this one will allow the promotion of a stronger adhesion between the substrate and also the coating. So if we look at portion C here, is that if the worst case, if there is any incomplete or gap between the solidified coating and the contact area, it will actually reduce or resulting the weak spot where the water and contamination can permeate into this cavity and cause erosion or corrosion, delamination. So if we see here the adhesion mechanism of a ceramic coating, a good adhesion requires the chemical bonding, mechanical bonding, and also the thermodynamic influences. If we look into thermodynamic influences, we are looking at the environmental and the surface energy effect. Mechanical bonding, we are, as discussed in detail earlier a bit, is the interlocking and the surface roughness effect. If chemical bonding, we are looking at the primary or the secondary bond, meaning is it they're having a metallic bond, ionic bond, or even van der Waals force of adhesion. So these are actually the core concept of defining a coating attachment or adhesion. So we look at the next one is more on the surface roughness. The surface roughness, this is a continuation. So what is the optimal surface roughness for the coating method? It depends. If we look into thermal spray coating, we actually require 2 to 8 micron of the surface roughness in the scale of RA for adequate ceramic adhesion. But if we look into vapor deposition method, PVD or CVD, we require only 1 to 3 micron of surface roughness. So if we look into the next surface requirement for the component is actually the CTE between the substrate and the coating, the coefficient of thermal expansion. So if we look here, the application of ceramic onto the cutting tool will reduce the buildup of heat due to the elevated temperature, which actually reduce the lifespan of the tool. The mismatch between the coefficient, that is the substrate and the coating, will actually leads to cracking, coating spalling occur under the thermal and the mechanical loading. So if we look over here, we compare between how the technique that we can use to mitigate the differences between the CTE is that if we're looking into multi-light coating, that is we can use plasma spraying process that actually lower the CTE reduction. If we look into Zircon intermediate layer, that is more, I would say is a medium layer, we actually can use wet chemical process that is having a better CTE matching. So there is no right or wrong, it just depends on what is the application and what processes that we are looking into it. So the next surface requirement for the material, the substrate, is actually the substrate mechanical property. So if we look at the pillar here, we actually require first the hardness, second the tensile strength of the material, and also the wear resistance of the material. So a suitable substrate ideally must have the high hardness, tensile strength, and wear resistance to actually withstand the lifespan against the machining parameter, that is the speed and the environmental condition. Tungsten carbide, WC, and also high speed steel, HSS, are commonly used and they have favorable condition as mentioned. So we look into the next portion on the surface preparation. So if we look into surface preparation, we can see that actually there is 5 portions. The first one is actually we need to identify the need for surface preparation. So we need to see what kind of surface preparation we are looking, what kind of coating we are looking for. Then we are looking into the next one. We need a clean surface by removing the contaminant and to ensure a clean base or a clean substrate surface. Then we will look into the treated surface layer, that is applying method of altering the surface structure. Then we followed by number 4, we apply the coating, that is a deposition of a film onto the prepared surface layer. And we also need to do the last checkpoint on by ensuring the coating integrity, by checking for any adhesion or absence of pinholes. So under the surface preparation, we are looking this we will okay maybe I skip. Okay, we look into one portion of the surface preparation. So the first one is actually we are looking into abrasive cleaning. So we are looking into specifically grit blasting process. So grit blasting process, how do we look this slide? We look from the from the bottom to the top. So we have stress induction, surface roughening, contamination removal, surface deformation, particle entrainment, and the last one we do the grip particle acceleration. For chemical etching, the next process we are looking into the removal of large amount of oxide. Usually because we are using steel, oxide formation is, I would say, unavoidable. So this formation on the metal during metal fabrication process formed during the metal fabrication is also known as pickling, meaning the process to remove this oxide is known as pickling. So alkaline, we use alkaline first before acid pickling in order to get a uniform wetting and etching. The preferential etching and the grain boundary form as a result of etching two-phase system. So mount picking is also known as bright dip. So if we look at here, acid cleaning of the metallic has negative effect by it of introducing hydrogen onto the surface, which actually can embrittle the metal and the ceramic. So if we look at here, this is the metal surface treatment process that is from the metal formation of oxide up to the hydrogen embrittlement. If we look into the next process of surface cleaning, we also have to look into ultrasonic cleaning. So how ultrasonic cleaning works is actually they are actually inducing a low frequency ultrasonic on a jetting action of collapsation of the cavity bubble on the contamination with the surface by providing high pressure jet fluid against the surface. This method is actually to use to remove loosely adhered particle after grinding and abrasive procedure. That is the first two procedure. And the clean surface with solvent to remove the absorbed contaminant. So the cavitation bubble are formed by the tension wave propagation of ultrasonic wave in the fluid medium. So if we look over here, usually ultrasonic cleaning will be deep into a chemical that industrial chemical they will call it as the RBS. That is a very high alkaline solution, and the parameter is that they will use high alkaline solution followed by high temperature for the cleaning. If we look over here, the ultrasonic cleaning, the initiation of the ultrasonic wave in the ultrasonic tank bath, then this formation of the cavitation actually they will attach to the contamination and it will collapse. Once they collapse, actually the main aim is actually to break away the contamination. Then if we see here the collapse of the cavitation bubble followed by the jet action of the cleaning and the removal of this particle on the surface.
Thank you, Andrew. Now come to my part here. I will present this suitable surface modification process. So a frequently used coating system deposited by CVD is titanium carbonitride and aluminum oxide, which this titanium carbonitride is representing the base layer and aluminum oxide is the top layer. The deposition by CVD is accompanied by the development of a dermal tensile crack network formed during cooling after coating deposition due to mismatches of the thermal expansion coefficient of a cemented carbide and the hard coating layers. The formed cracks offer a pathway for diffusion of a specified specimen from the ambient through the coating part, but also from the coating layer and the cemented carbide substrate towards the surface. This diffusion process fosters oxidation of the cemented carbide, but also of the titanium carbonitride base layer at machining conditions. Chemical vapor deposition (CVD) is usually activated thermally, okay, so by high temperature or by laser assistance. Gaseous precursors, okay, like nitrogen, chlorine, are introduced into the deposition reactor, where the coating is deposited from the precursor mixture applied at elevated temperature. The precursors can be initially solid, liquid, or gaseous. Solid precursors like aluminum, zirconium, or titanium had to be primarily evaporated to be transported into the reaction chamber. This can be achieved by chlorination. And subsequently, the growth of thin film by CVD methods, where material transfer from the vapor phase condensate on a substrate, can be summarized by 3 steps. First, okay, incident atoms impinge on the substrate surface. They are either refracted, or if they lose enough energy to the substrate lattice, they become loosely bonded atoms. Second, the atoms diffuse over the surface and exchange energy with the lattice and other atoms or molecules until they are either dissolved or trapped at low energy sites. Third, incorporated atoms readjust their position within the lattice by Park diffusion. This process strongly depends on the applied conditions, the substrate temperature, or the pressure during deposition. Surface roughness and defects in the surface near zone of the substrate are of major impact on film growth, since nucleates are preferably formed on lattice defect, atomic step, or scratches in the surface. The diagram here is showing that, okay, is the island grow and also layer by layer grow, and the third mix layer and island grow. So the structure of the coating actually have a 3 zone. In zone 1, okay, the film structure consists of a columnar crane, okay, which are capped by a dome-like top. This structure is a result of a film growth at high temperature. Additionally, higher film thickness aggregate this effect to specify the crane size increase, and the columnar crane become more pronounced with increasing film thickness. In zone 2, the structure is also columnar but more faceted and angular. In zone 3, the film consists of 5 equal X cranes. 5 crane structure can be obtained at low temperature, high supersaturations of the vapor phase, and at low pressure, at conditions where diffusion processes are minimized.
So the next slide is about pros and cons for CVD coating. So we go for pros first, advantage first. So it provide dense and pure coatings, which is very good, which means that it provide low porosity and also low impurities coatings. And then the second one is it provide uniform films, because CVD operate at 500 and also 1000 degrees Celsius, so it's chemically and metallurgically bonded with the substrate, which provide a strong adhesion coating. And also for the third one also, it has non-line of sight deposition and also high throwing power. Is also for uniform films also. And also it has precise control, which means that the parameter is very easy to control. And also lastly, it is cost effectiveness, which means that because CVD does not need ultra high vacuum to operate compared to PVD, so the cost is lower compared to PVD. And also for one machine we can use metal, oxide, carbide in one machine, no need to buy another machine, so it's versatile. So we go for the cons, for the disadvantages. So first, stress in films, because CVD operate at high temperature 500 to 1000 degrees Celsius, so it introduce stress at the films. So crack may appear on the films, so which can cause oxidation and wear faster, which may reduce the lifespan of the tools. And also the second one, because CVD use gas precursor such as silane, hydrogen, so it need to follow strictly follow procedure on how to handle, how to store the gas, and also how to dispose it. We need to follow procedure of disposal from our country. And then this gas also can be toxic to human and also environment, so it's very very dangerous if we exposed to these gases. And then the third one is actually expensive equipment. This one is actually for investment during investment cost. It's quite expensive, this machine. And then the last one is high energy use, because this CVD coating operate at high temperature, so it require high electrical energy. So that's all for the pros and cons. So for the next slide is about characterization and tests used to investigate the performance of the components. So here we will discuss on how to characterize CVD coating. So for the CVD coating, first coating is made up of aluminum oxide, and then the base is actually made up of titanium carbonitride. So for the first characterization is surface morphology by scanning electron microscope. So SEM is actually commonly used to analyze coating microstructure, which focus on grain size, shape, and coating uniformity. So as you can see that from the SEM images, there is 1A. Actually, the coating sample has a lot of tiny holes, which indicates that the coating sample has high porosity. And then we have 1B. The grain size show that it has a large grain size compared to sample second B. The grain size is much smaller compared to 1B, so we can see that there is difference on the grain size, which may indicates that the sample might experience different nucleation treatment. So the next slide is about surface morphology also, but now using transmission electron microscope. So actually TM provide a better resolution than SEM, which enable in-depth examination of interior microstructures such as voids and also phase interfaces. So as for example, we have a TEM images, so the same sample also. For coating 1A, we can see that there is beam scattering there. So wait a minute. So you can see here there is beam scattering there, which indicates that there is a high porosity there. There is possible crack there. So the coating is actually has defect there. So when we compare to the second sample 2B, it's actually no beam scattering, and also there is smooth layer there, and then it's compact. So it actually indicates that there is nearly flawless coating, which is very good. So for the next method is actually elemental composition analysis by EDX, or the longer name is energy dispersive X-ray. So EDX is actually, when we use SEM, we have EDX also. EDX is actually for elemental analysis. So we can, for the aluminum oxide coating, actually we can confirm for EDX we can only confirm the element only. We cannot confirm the compounds. so from the EDX analysis, actually we can have a rough idea on what coating material it is. So for example, we can see that from the analysis here, so we have a high percentage of oxygen here, and then we have also high percentage of aluminium here. So we can have a rough idea is actually what type of coatings there through the result of the high oxygen and also aluminium, which we can maybe have a rough idea which is aluminum oxide. So the others is actually maybe impurities here, sodium and also magnesium. Is maybe contamination of impurities during coating process. So for the next method is actually phase analysis by XRD. So the longer name is actually X-ray diffraction. So XRD is actually to compare diffraction patterns of sample with software reference pattern to determine crystalline phases in a sample. So depending on the crystal structure, each phase generates a different set of diffraction peaks. So it has their own unique peaks to determine what type of materials it is. So the same sample also, we can see that the red one peak is actually for the coating, is actually it indicates aluminum oxide. So the black one is actually the base, actually is actually titanium carbonitride. So actually compared to EDX, which is elemental analysis, XRD actually can show a compound materials. So here we can straight away know, oh, this one is the coating is aluminum oxide, so the base is titanium carbonitride. So compared to EDX is only element only, aluminium and also oxygen only. So from here we can have can confirm what type of coating and also substrate used for this sample. So the last characterization method is hardness testing by nano indentation. So hardness testing is actually to evaluate a material resistant to deformation. So since CVD coating has micrometer coating thickness, so the best or the most suitable hardness tester you need to use is actually nano indentation. So this method measure Young's modulus and hardness of surface layer at depth from nanometer to microns using a dynamic load over time. So as we can see that from the hardness result, we have load and also we have displacement or depth. So we have three types of layer: aluminum oxide, silicon nitride and also silicon oxide. So from here we can see that aluminum oxide, the red one, it has a high hardness result compared to others, which indicates that it also has a wear resistance. So from the graph is actually when we apply high load on aluminum oxide coating, so the depth or the displacement of the aluminum oxide is much smaller compared to other coating layers. So that is how the hardness result is interpreted. So as a conclusion, CVD coatings benefit to ceramic cutting tools by enhancing their hardness, wear resistance and overall performance. So this technology helps improve the durability of the tools, making them more suitable for high speed and precise machining tasks. For sustainability, is actually CVD coating extend the tool's lifespan, reduce the need for frequent replacement and boost the quality of the finished product. As industry continue to demand higher efficiency and performance, CVD coated ceramic cutting tools will remain a valuable solution to meet these needs, offering reliable performance, a range of machining application. So that's all from us, Group 6. So thank you.